So we are continuing with our paper that we got from Math Squared, Materials Mathematics. And this is a paper by Howard Weiss or Howard Howie Weiss. It's a simple SIR model, and then it is applied to public health. So it means there is some disease that we are going to apply this model on. So the SIR model and the foundations of public health. We are like connecting mathematics and public health, and this is possible. And what we did back then, which we just want to level up and make sure that we are all on the same page, we had the model. This is the SIR model. And some of you hear me talking about compartments, and you might be wondering what it is that I'm talking about. But we are simply saying that we have got the group of susceptibles in here. So we've got S, and then they become infected. Then we've got I. Then they recover. So we've got R, like that. All right. So let me just do this so that we can see what we're doing here. So then we are simply saying that if you are susceptible, you move from being susceptible at a rate beta Si. So the rate is given by this guy. This is the interaction of the susceptibles and the infected, which causes that the number of susceptibles becomes less as they move to being infected, to the infected compartment. That's why our equation, our first equation is ds dt is equals to minus beta Si. It means that we are moving from here. That's why we've got a negative. We are moving from here and we are going to the ith compartment. All right. And then from the ith compartment, there is a movement. Let's see. So there is feeding into I, which is what we have got there, but taking from S. And there's also taking from I, feeding into R. So I can tell you now that I itself is receiving, but it's also losing. It's because people are recovering at a rate V or nu. All right. So that is the other thing that is happening here. And then R is receiving. The recovered compartment is also receiving. The R, the T is equals to VI. It is receiving this into that. So this is the situation that we have got. All right. And we have got this term that we explained, and we are going to explain again because it is very important for you to understand that. Actually, if we look at it, we call it, in epidemiological terms, we call it the force of infection, which represents the rate at which susceptible individuals become infected per unit time. So it is like the measure of the risk of transmission from infectious individuals to susceptible ones. And mostly in mathematics, we use lambda to represent the force of infection. So what do we have? We have got this explained here. It is explained in full here, where they said, look, maybe we have got infected individuals that have got K contacts, and each sufficient for transmission. Each contact is sufficient for transmission per unit time. And it doesn't matter how many people are in the population, what the size of n. So the size of n doesn't matter. All right. K contacts irrespective of the size of K. Then we have got KSN or S over N, right? Ks over N of these contacts. So we are simply saying that, look, of our population N, we have got this ratio of susceptibles, S over N. These are the susceptibles. This is the ratio of the susceptibles in our total population. And then for that ratio, we are saying that each individual has got these K contacts. So in other words, if we multiply K by S over N, what we get is the number of contacts of each individual proportional to the number of susceptibles in the total population. All right? That's what we have. But then we also are interested in the fraction tau of adequate contacts resulting in transmission. So being in contact is one thing, but contact that yields transmission is what we are interested in. So we end up having K tau S over N. And if we take now K tau over N, right? K tau over N. This is our force of infection. That's what we are talking about. This is our force of infection. And as we have described it, we said it is some sort of rate at which susceptible individuals actually become infected per unit time, measuring the risk of transmission from infectious individuals to susceptible ones. Remember, we have got people that we know, and then contacts that actually result in transmission. So we have got fraction tau of adequate contacts that result in transmission, and we've got K contacts from the susceptibles that we know, and infected individual knows. So we've got those two things. So in simpler terms, the force of infection is the proportional to the product of the transmission rate and the prevalence of infectious individuals. So we'll talk about the prevalence of infectious individual in a moment. So what we are going to do now is we are going to say, look, we have got this model. What is it going to tell us about the dynamics of the propagation of the disease? Is it going to die out? Is it going to be there always? Are we going to ever have a disease-free equilibrium where we don't have the disease at all? So those are the things that we want to look at based on this particular model that we've got before us.